Hi everyone, let us continue the topic atomic structure, right? In view of the shortcomings in Bohr's atomic model, several attempts were made to give a more suitable and general model of atoms. One of such developments was given in uncertainty principle, okay, given by Heisenberg. Now our topic is Heisenberg's uncertainty principle, according to which it is impossible to determine simultaneously the exact position and exact momentum of a fast moving particle like electron. Means this is applicable for electrons, such particles, microparticles only. Once again, what's the definition given for uncertainty principle by Heisenberg? It is impossible to determine the exact position and exact momentum of a fast moving particle simultaneously. It is impossible to determine simultaneously the exact position and exact momentum of a fast moving particle like electron. Mathematically, it was expressed as delta x into delta p greater than or equals to h by 4 pi. Here, delta x indicates uncertainty. Delta x indicates uncertainty in position, whereas delta p indicates uncertainty in momentum. Means uncertainty means not knowing the momentum properly, accurately. Uncertainty means not knowing the parameter accurately. Now, this is the mathematical expression for Heisenberg's uncertainty principle. Let us illustrate this once. Suppose if position is known, in case if position is known accurately, then uncertainty in position, that is delta x, will be nearly zero. There won't be any uncertainty, or uncertainty will be small, right? Or nearly zero. Suppose let us take uncertainty 0. Position is known accurately, no? Then there won't be any uncertainty. Then this expression delta p is equals to or greater than or equals to h by 4 pi into delta x. As position is known accurately, its uncertainty will be 0. H by 0 is nothing but infinity. So this infinity stands for which value? It is for uncertainty in momentum. So if position is certainly known, then uncertainty in momentum is such a big value which is equals to infinity. So if position is known certainly, then its momentum will be highly uncertain. Similarly, if momentum is known, suppose if its momentum is known accurately, let us take momentum is known accurately, then as momentum is clearly known, there won't be any uncertainty in its momentum, right? There won't be any uncertainty in momentum. Delta p will be 0. Then uncertainty in position can be expressed as h by 4 pi into delta p, that equals to h by 0. Again, this is also equals to infinity. Means if momentum is known certainly accurately, then uncertainty in position will be very high and is almost equals to infinity. In this way, if one is known certainly, other one cannot be determined with accuracy. So this is called as Heisenberg's uncertainty principle. Once again, let us go through the definition part. What does it state? It is impossible to determine the exact position and exact momentum simultaneously for a fast moving particle, or exactly the same definition also we can give. It is impossible to determine simultaneously the exact position and exact momentum of a fast moving particle like electron. As momentum can be expressed as momentum p is equals to mass into velocity, Uncertainty in momentum delta p can be expressed as mass into uncertainty in velocity. By substituting this equation in Heisenberg's uncertainty principle, we can write it as delta x into delta p greater than or equals to h by 4 pi can be given as delta x into m delta v greater than or equals to h by 4 pi. So we can get a relation for the product of uncertainty in position and uncertainty in velocity as h by 4 pi m. This is also other form of Heisenberg's uncertainty principle. We can get different expressions. Delta x equals to h by 4 pi m into delta v. Similarly, delta v equals to h by 4 pi m into delta x. Right. In this way, if velocity is certainly known, if the velocity of moving electron is certainly known, its uncertainty will be 0. Then when this is 0, uncertainty in position will be something by 0, infinity, very big value. Same way as we discussed earlier. Similarly, if position of an electron is certainly known, accurately known, then its uncertainty will be 0. Then uncertainty in velocity will be as high as infinity. In this way, we can explain, we can illustrate this Heisenberg's uncertainty principle. Now, we can also discuss this uncertainty principle. We can understand this uncertainty principle by taking an example. Suppose if you are asked to find out the thickness of a sheet of paper using a scale calibrated with 1 millimeter reading. If you are asked to find the thickness of a sheet of paper which has a 1 millimeter reading, right? Will the obtained values are meaningful? No, definitely those obtained values are inaccurate and meaningless, right? Because sheet of paper is less than 1 millimeter thickness, whereas the normal scale contains smallest reading as 1 millimeter. So we need such a scale which is calibrated with the units less than the thickness of the sheet of paper. Analogously, we can discuss like when electron position is to be determined. Analogously, when a position of electron is to be determined, we need such a meter scale calibrated with the dimension smaller than the dimension of electron. Of course, electron is considered as a point charge and is basically dimensionless. But still, conceptually we are discussing. So, to find out the position of an electron, we have to illuminate the electron with a light which is nothing but stream of photons. Now, when a high momentum photon strikes an electron, what happens? Momentum is equals to h by lambda. So from de Broglie's wavelength equation, we are getting this expression. When a high momentum photon strikes an electron, definitely that because of that illumination happened there, position can be determined with accuracy. But with no doubt, its velocity will be definitely uncertain, because when a fast moving electron, suppose this electron is moving around the nucleus in this way. When this electron is illuminated with a light beam, see, this is a photon striking the electron. So when this photon strikes, that illumination takes place. Because of the illumination, we can find that here is the electron. But at the same time, the electron which absorbs the energy of photon will change its trajectory, will move out of its path. Okay, because of possessing more energy, its trajectory will be changed. Right? In this way, the path in which electron is moving is not fixed circular orbit. So with this, the fixed circular orbit concept given by Niels Bohr was almost ruled out. Let us see the significance of this uncertainty principle. The first significance was it ruled out the existence of fixed circular paths or trajectories of electron and other such particles. Just now we discussed about this ruled out. Okay, it was ruled out because of a change in trajectory by the incidence of light. Next significance was the effect of the principle is significant only for microscopic particles. The effect of principle is significant only for microscopic particles like electrons, and is almost it is negligible or invalid for macroscopic particles and objects. For example, if uncertainty principle is applied for an object of mass 1 milligram, if it is applied for an object of mass 1 milligram, 1 milligram means 10 power minus 3 grams, means 10 power minus 6 kg. Then product of uncertainties of position and velocity can be given as h by 4 pi m. H is Planck's constant, whose value is 6.625 into 10 power minus 34 joule second, and 4 into pi value is 3.14, and mass of the object is given as 10 power minus 6 kg. On simplification, we will get this product of uncertainties of position and velocity as some numerical value into 10 power minus 28 meter square per second. Okay, so uncertainties product is of order 10 power minus 28, means it is very less. Uncertainty is very less, extremely small, means we cannot determine its uncertainty properly, and is insignificant also. Thus, we can say, one can conclude that in dealing with 1 milligram size or heavier objects, associated uncertainties are hardly of any real consequences. And when it comes to the case of microscopic particle, just now we discussed a macroscopic particle, for example 1 milligram size, okay, mass. In case of microscopic particle like electron, we are aware of the mass of electron, right? It is 9.1 into 10 power minus 31 kg. Product of uncertainties of position and velocity is given as h by 4 pi into mass of electron. On substituting the values, this product was observed as 10 power minus 4 meter square per second. That is, if one try to find out the location of an electron, suppose to an uncertainty of 10 power minus 8 meters, suppose, then uncertainty in velocity delta v can be expressed as 10 power minus 4 over 10 power minus 8, means approximately or around 10 power 4. It is of the order 10 power 4 meters per second, which is so large. Uncertainty in velocity is such a large value that the classical picture of fixed circular paths given by Bohr cannot hold good from this, right? This is a numerical from Heisenberg's uncertainty principle. See, a microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstroms. Within a distance of 0.1 angstroms. What is the uncertainty involved in the measurements of its velocity? Means uncertainty in position is given, uncertainty in velocity is asked to find out. So we have to apply the principle, Heisenberg's uncertainty principle. First of all, let's get the data within a distance of 0.1 angstrom. So delta x is 0.1 into angstrom means 10 power minus 10 meters. 10 power minus 8 centimeters, 10 power minus 10 meters. This is given. And to locate an electron, what is mass of electron? It is 9.1 into 10 power minus 31 kg. And we are asked to find out uncertainty in velocity. So let us apply this Heisenberg's uncertainty principle, which is given as delta x into delta v equals to h by 4 pi m. So we need to find delta v, that equals to 6.625 into 10 power minus 34 joule second over 4 into pi value is 3.14, we are aware of. And mass of electron is 9.1 into 10 power minus 31 kg into delta x. Also we are taking this here to denominator. Delta x is given as 0.1 into 10 power minus 10. 0.1 into 10 power minus 10 meters. So this is on cancellation, it is 10 power minus 9 meters, right? On substitution and calculating everything, see, it is 6.625 into 10 power minus 33, 10 power minus 3, suppose cancel, this is 10 power minus 3 over 4 into 3.14 into 9.1 into 10 power minus 9. On simplification, this is joule means kg meter square second inverse square. Don't neglect this conversion. You need to remember 1 joule is equals to kg meter square second inverse square. Kg meter square second inverse square, and 1 erg is equals to gram centimeter square second inverse square. Okay, one should be very perfect in these conversions. Now kg meter square second inverse square over kg and meter. Right, here second is also there. Now kg is cancelled, 1 meter is cancelled, 1 second is cancelled. So answer will be in terms of approximately 0.579 into 10 power 7 meters per second. On further simplification, uncertainty in velocity can be expressed as 5.79 into 10 power 6 meters per second. Okay, so this is one numerical from Heisenberg's uncertainty principle. It's a mere substitution of the given values, that's it. This is another question. A golf ball has a mass of 40 grams. Mass is given. Don't worry, it is a macroscopic particle. Let us see once again whether Heisenberg's uncertainty principle is ruled out for macroscopic particle or not. Has a mass of 40 grams and a speed of 45 meters per second. Its velocity is given, mass is given. So, solution, mass is 40 grams, that is 40 into 10 power minus 3 kg. Now, what else is given? Velocity is given as 45 meters per second. Then uncertainty in velocity is 2% of 45, that is 2 by 100 into 45 meters per second, that is 0.9 meters per second, 90 by 100. No. Now, if the speed can be measured with an accuracy of 2%, calculate the uncertainty in position. So, what we have to find? We need to find out delta x. Right? Now, what's the relation? We have delta x into m delta v is equals to h by 4 pi. Delta x into m delta v is equals to h by 4 pi. Now, substitute. We need to find delta x, that equals to 6.625 into 10 power minus 34 joule second over 4 into 3.14 into mass of electron is 9.1 into 10. It's not electron, no. It is 40 into 10 power minus 3 kg into delta v, uncertainty in velocity is given as 0.9 meters per second. So, we need to convert, as we discussed earlier, this is 6.625 by 4 into 3.14 into 40 into 0.9. So, 10 power minus 34 and minus 3, if you cancel, 10 power minus 31, this is a kg meter square second inverse square instead of joule into second by kg meters per second. So, per second is cancelled, second square is completely cancelled, 1 meter is cancelled, kg is cancelled. So, on simplification, it will be around 1.46 into 10 power minus 33 meters. So, this is almost, what's the size of nucleus? What's the size of nucleus is 10 power 15 order, right? It is of order 10 power minus 15 meters. Nucleus is of order, size of nucleus is of order 10 power minus 15 meters. When compared with this, this is 10 power minus 18 times, right? So, which has no meaning. Thus, these for larger objects, uncertainty principle had set meaningless limits. It has not given any meaningful limits for this larger objects. See, this is another question. If the position of electron is measured within an accuracy of plus or minus 2 into 10 power minus 3 nanometers, calculate the uncertainty in momentum of the electron. Suppose momentum of electron, actual momentum of electron is given as h by 4 pi into 0.05 nanometer. Is there any problem in defining this value? So, that's the question. So, what we have to do? We have to find the momentum, uncertainty in momentum, and compare that uncertainty with the given momentum. Whether this given momentum is applicable or not, we have to find it out. Now, let us see. We have uncertainty principle formula as delta x into delta p greater than or equals to h by 4 pi, right? We are given with uncertainty in position as a plus or minus 0.002 nanometers, means on simplification it is 2 into 10 power minus 3 nanometer means 10 power minus 9. So, 9 and 3. So, 2 into 10 power minus 12 meters. Now, we are asked to find out delta p, uncertainty in momentum. So, find it using the formula h by 4 pi into delta x. This is joule. Instead of joule, I substituted kg, meter square and second inverse square. On simplification, see 4 pi and uncertainty in position is 2 into 10 power minus 12 meters. We got this uncertainty in momentum as 2.63 into 10 power minus 23 kg meter per second. Kg meter per second. Now, this is the calculated uncertainty in momentum. But actual momentum given in the question is h by 4 pi into 0.05 nanometer. Let us substitute this also. Let us find the exact value of this also. H by 4 into 3.514 into 5 into 10 power minus 11 meters. And on substituting and calculating this, we got this value 1.05 into 10 power minus 24 kg meter per second. When compared with the actually determined uncertainty momentum, this is very less, right? Which is impossible practically. That's why this cannot be taken as actual momentum. So that's what the conclusion given, as this value is smaller than the calculated uncertainty in momentum, which is practically impossible. This value cannot be given as actual momentum. So these are some questions from Heisenberg's uncertainty principle, and the rest we will solve it in worksheets given, right?